All right, today we're jumping into something that sounds like it's straight out of science fiction. We're talking about a concept that could completely flip how we think about creating software by turning pure logic directly into working code.
And I don't just mean, figuring out a tricky algorithm. I mean, what if the very act of solving a logic puzzle was in itself the act of writing a program?
Yeah, I know. It sounds pretty wild, right? But this is a very real and honestly a mind-bending area of computer science. The idea is that a logical proof doesn't just describe a program, it can be literally transformed into one.
So, how on earth does this actually work? Let's peel back the curtain and uncover this secret connection, this hidden code that lives inside the world of mathematical proofs. Okay, the magic key that unlocks this whole thing has a pretty fancy name, the Curry-Howard Isomorphism. But don't let the name scare you. You can just think of it as the Rosetta Stone for this field. It's what lets us translate the language of logic into the language of computation. It's this deep, fundamental connection that makes everything else possible.
And this is where it all clicks. It's a perfect one-to-one mapping. On one side, you have a logical formula, something like, for any input A, I can produce an output B. Well, in programming, that's just a data type. But here's the incredible part. The step-by-step proof that you create for that formula, that becomes the program. The proof is the algorithm. Let that sink in for a second. So the process is kind of like a three-step recipe. First, you write down what you want your program to do, but as a formal logic statement. Then you don't start coding. Instead, you build what's called a constructive proof that shows a solution has to exist. And then for the final step, you just run a process that pulls the actual working code right out of the structure of your proof. Okay, but that's the big question, isn't it? How does a bunch of static logic on a page suddenly spring to life and start computing? What's the engine here? Well, believe it or not, the secret is all about what you take out of the proof. It all comes down to a process called cut elimination. And honestly, the best way to get it is to think about a recipe. Imagine a cookbook tells you to make a master vinaigrette. That's a shortcut, right? It assumes you already have that other recipe. In logic, that's called a cut. Cut elimination is just the process of replacing that shortcut with the full recipe for the vinaigrette, pasting it right into the main one. The result is one long, super detailed recipe that anyone can follow from start to finish. And this gives us a really clear picture of the two types of proofs we're dealing with. A proof with cuts is like that first recipe. It's short, sweet, easy for a human to understand, but it relies on you knowing other stuff. But the cut-free proof, that's the whole shebang. It's way longer, yeah, but it's totally self-contained. It shows you the entire computational path, from the very first ingredient to the final dish. And listen, this isn't just me making up a nice analogy. The source material spells it out perfectly. The process of cut elimination, it is the computation. That act of expanding all the shortcuts is what transforms the static logic into a dynamic set of instructions, a real program. All right, so if this is so amazing, you're probably wondering, why aren't we all doing this? Why don't we all just write proofs instead of code? Well, like any big, powerful idea, there's a catch. A pretty big one, actually. Here's the problem in a nutshell. Those shortcuts, those cuts that make proofs elegant and readable for us humans, they're fantastic, but getting rid of them to create something a computer can run, well, it comes at a very steep price. And I mean a huge price. Just look at this. You can start with a neat, tidy little proof. But once you run it through that cut elimination process to make it executable, bam, it can just explode in size. We're not talking about it getting a little bit longer. We're talking about it becoming astronomically bigger, so big that it becomes totally impractical. So that's the big trade-off we're stuck with right now. On one hand, you've got these beautiful, concise proofs that we can actually wrap our heads around. On the other, you have these massive, sprawling, but fully executable versions. The holy grail for researchers in this field is finding a practical balance, a way to manage this computational explosion. But don't think for a second that this problem has stopped people. Not at all. This is a super active field of research, and what's coming over the horizon is really, really exciting. And let's be clear, we're not just talking about dusty old theory books anymore. This stuff is being put into practice. There are actual tools being built, like the GAPT framework mentioned in the source material, that are designed to wrestle with exactly these kinds of proof transformations and make this a practical reality. So what's the big deal? Why should we care? Well, the ultimate prize here is the potential for perfectly correct software. I mean, if your program comes from a mathematically sound proof, it is, by definition, bug-free according to its specification. This could automate huge, complex parts of coding, and honestly, it gives us a much deeper understanding of what computation even is. Which leaves us with a fascinating thought for the future. As these techniques get better, will the line between a programmer and a mathematician just disappear? Are we heading for a future where developers spend their days not just typing code, but crafting elegant proofs that bring perfect software to life? Now that is something to think about.